So as an example, let's say we are given a set of vectors V. So from the very beginning, it's simply just a set of vectors. V is a set of vectors in R2. It's a set of vectors such that the components of the component 1 equals component 2. Or you can understand that it's the vectors with two components where they equal each other. They equal each other. So commonly with this kind of problem, once the set description is given, then we are asked to simply determine if V is a subspace of R2. But in the end, as I said earlier, subspace, being a subspace, is in the end a vector space itself. And this question at first seems like it's only simply a yes or no question. You're just saying yes or you're saying no, but it's going to be the whole, an entire, it means we're going to need to bring up an entire proof to either say if it's a yes or if you're going to say a no, any of these answers here has to come with a proof. And so I would say yes, this is a vector space or a subspace of R2 simply because any of these is already a vector in R2 as a vector space. And then itself basically being a smaller set, a subset. Now once we can prove that this is also a vector space being smaller level than the R2 vector space, then this is why it's called a subspace. But so here's how I'm going to apply the Professor Streng's philosophy into proving this, and with that, with what I have pointed out earlier. So as long as, now I shouldn't say that too early, but let's now start out by, I'm going to let V and W be two vectors that are from the set V. And right now we haven't proven that it's a vector V yet. So I'm saying yes, but I have to prove my statements. I have to prove my statement saying that V is a vector space. So to prove my statement saying V is a vector space, or more specifically a subspace of R2 over here, then I first start out, or generally we first start out with any two vectors, arbitrary vectors from the set V right here. So at this point right here, we don't know if it's a vector space yet. We only say that it's a set of vectors. Then all we need to do is create some arbitrary, and now I'm going to consider further that some two scalars, C and D, are being values in real. Being just any two values in real. So keep in mind they can be negative, any of these can be negative. They can both be zeros because the real lines contain all kinds of values. So we're just not talking about complex numbers here yet. But so that means these are also arbitrary. So now I'm going to create an arbitrary linear combination. So any linear combination of V and W is going to look like as following. So CV plus W plus DW is going to look like that. And so now let's develop that further. The point now is that we need to also, the goal is we need to prove that this is also, so I'm putting a little note here, need to prove that this linear combination, any arbitrary linear combination is also a member in that set V. And once that can be done successfully, we are good to go, or we are done with our proof. So that's why let me now roll back to my beginning point here. And so I'm going to consider it just, so I'm going to say let CV plus DW be a linear combination. And once we say that this is a linear combination, and let's develop it out a little further. So let's break it down to their components. So now C times V and means V, generally we've learned in any linear algebra class, we can call that V1 is the first component, this is V2, so CV is the same as the scalar C times with the column vector V1, V2, plus, and now the scalar C is multiplying with the column vector W1 and W2. And so now the usual addition for vectors that we've learned is going to allow us to bring to the next step. And I'm not saying anything about whether we know if these two are in the set V yet. We're only saying that this linear combination we keep working out further and rewriting them in different expressions. So that means I'm going to have and we're going to have CV1. Allow me to go in slow step a little bit with first vector after the scalar becomes CV1 with CV2 plus dW1 and dW2, and if any of you viewing this video is not happy with this step, you can jump to the next step, and I'm getting there. And then continuing with that work, we will end up with, so this here together as one vector is going to look like this. First component of our sum vector is going to be CV1 plus dW1. And next component 2 is CV2 plus dW2. And so now this is one vector where the first component is a combination again of these two first components of V and W. And also component 2 of this final vector is a linear combination of second components of V and W. What we want to know now is, will this be a vector also in our set V? So as long as you can prove, because remind yourself that V is the set of those vectors where the requirements here says first component equals second component. Meaning, if you want to prove this final vector to also be in V, all you have to do is prove that these two components are also equal to each other, satisfying the only requirements for being in the set V. And so now, here's how we start. We already knew that since V and W are all from V, then, of course, V1 equals to V2. That's no doubt about it. No one can argue. And then, in that case, and also, at the same time, is W1 must be equal to W2. No one can argue about these. Then in the next step, consequently, and in the rule of algebra, if now each of these equality, if we multiply the top one here, V1, V2 equals V2, but we multiply with a scalar C to both sides, doesn't matter if C is a 0, or doesn't matter if C is a negative, or being a positive, multiplying one same value to both sides of an equation ends up with the same equation. And in the same way will happen here, we're going to consequently lead to dW1 must equal to dW2 for whatever value of D is. And so now, from this point, I am going to, side by side, add these two sides of my two equations. So that means if adding the left side together, we're looking at CV1 plus dW1. And on the other side, and here we, for sure, the rule of algebra says we can have equality maintained here. CV2 equals CV2 plus dW2. Fabulous. What have we brought to themselves here? We have now just proven that, and so observation now tells us that this left-hand side of our equality we have just proven is the first component of our final vector just earlier. And the other side, or the right-hand side of our proven equality here came out is exactly the second component of our final vector. So in that way, what does it say here? Or what does that mean here? It means our final vector. So the impact now says the final vector V1 plus dW1 and CV1 plus dW1 and CV2 plus dW2 as a vector Now we know that this vector is also in V as well. Or as a general impact, this as an arbitrary linear combination of V and W. Any arbitrary linear combination of V and W is also in V. And therefore, our last powerful statement, therefore, V is a vector space. And furthermore, a subspace of R2. And that is the end of the proof. And in this example, let's say we are given a set of vectors V to contain all of those vectors with two components or vectors from R2 such that the requirements of that 2x minus y equals 1. So this relationship basically says first 2 times the first component of the vectors of any vector member here minus the second component with coefficient 1 equals 1. So that's the requirement for these vectors, for any of these vectors being a member of the set V. And similar question, let's say we want to determine if V is a subspace. So essentially it is can it be a vector space or not? And once it is a vector space, then it's a subspace of R2. And so right at first sight, again, this seems like an easy question, especially on many of the online homework assignments in these days. That then the answer that given either when you say yes if it fails, and it has to be no. But the trick, the entire art behind the scene now is that how can we prove if it's a yes for being a vector space, or how can we prove that if it's a no for not being a vector space? So in this particular problem, in this particular example, for this set of vectors, I would say no, it's not a vector space. So here's my proof. So remember, what's crucial here is that we have to start out with any two vectors. So let V and W be from the set V right here. If we want to prove that V is a vector space in general, then any linear combination of V and W have to once again being in V. But in this case, since I said no ahead of time that, hey, this is not going to be a subspace, it's not going to be a vector space, then we have to prove that, if we want to prove that this is not a vector space, then from any two vectors from V, we must prove that the plan here is we got to prove that there is a linear combination, at least one, a linear combination. CV plus DW that is not a member of V. And in common terms, usually we say that we disprove being a vector space by, as long as you can find a linear combination, we say that it's a, this is also the method as we say we're coming up with a counter example. All right, so I already said ahead of time that no, this set V is not a vector space. So let's now find a counter example to prove that there is a linear combination as a linear combination that's not inside of V. Well, so I can think of the two scalars, let's C equals 1 and D equals 1. And so if C equals 1 and D equals 1, these two are scalar. So CV times dw is exactly going to be just V plus W. And V plus W is the same as V in its truest form, in R2 form, V1, V2, plus a W1, W2. And further, this is going to be, and here I'm just talking about the expression, the manipulations around V and W. So here we're looking at the sum vector here must be consequently V1 plus W1, V2 plus W2. And so I am going to prove that this vector is actually not inside of V, is not a member of V. So this is what we know. We already knew that V and W are all vectors from V. So of course, 2V1 minus V2 must equals 1. This is the requirements for vector V to be inside of the set V, the set capital V. The same with W. The two components W1 and W2 must satisfy 2W1 minus W2 to equals 1 as well. So it's all because we chose V and W intentionally to be from vector, to be from the set V like that. But so algebraically again, so algebraically, the rule of algebra allows us to add the two equations here side by side. So left hand side added together term by term, we're looking at 2 times in parentheses V1 plus W1 and minus, here I can put it all in parentheses, V2 plus W2, and the right hand side becomes equals 2. And now what do we notice? Right here, after we add the two equations side by side, what do we notice? It looks like V1 plus W1 is the first component of our sum vector. V2 plus W2 is our second component of our sum vector. And this is 2 times first component minus 1 time of the second component. It looks like this is that left hand side part of the requirements to be inside of V. However, unfortunately, this is not equals 1. This is equals 2. So this is now indicating, so after seeing that, now we're making our final conclusion that V1 plus W1 and the second component is V2 plus W2 is in the end, it's now found to be not inside of the set V right there, simply because this requirement fails. And so that implies for us now that V is not a subspace, neither nor a vector space. And basically this is, I'm proving that it's just not a vector space, and then being not a vector space, and of course it's just not a subspace. And so we came up, the counter example we found here is that once we chose that example where scalar C equals 1 and scalar D equals 1, obviously we found one linear combination that is not inside the set.